Here's an example of capacitors in a circuit. The following circuit diagram is a simplified version of the flash circuit inside a disposable camera. The user charges the capacitor by pressing on a button, switch 1, and when the user snaps a picture, the shutter presses switch 2, which allows the capacitor to discharge quickly through the flash bulb. What is the time constant of the circuit when the capacitor is charging? What is the potential difference across the capacitor after one time constant? The flash bulb requires an initial potential difference of 350 volts in order to flash. How much time does it take to accumulate this potential difference across the capacitor? What is the time constant of the circuit when the capacitor is discharging? What is the potential difference across the flash bulb after one time constant? And how long does it take for the potential difference across the capacitor to drop to 10 volts? As usual, the first thing we do is copy the diagram. What I'm going to do is I'm going to leave the diagram up in a corner and let you look at the solution as I solve it, and then I'll show you the entire 2 pages. The time constant of a circuit is the resistance multiplied by the capacitance. By the way, you should be able to prove that ohms multiplied by farads are equivalent to seconds. 4 mega ohms multiplied by 2 nanofarads is 8 milliseconds. Next, let's find the potential difference across the capacitor after one time constant. For this, we need the formula for the voltage across a capacitor as it's charging. That's E multiplied by 1 minus e to the negative t over RC, which means that when the time is equal to the time constant, we get that the voltage across the capacitor is the EMF multiplied by 1 minus e to the negative RC over RC. E to the negative RC over RC is just e to the negative 1, which is 1 over e. 1 minus 1 over e is 0.632. So the voltage across the capacitor after one time constant is 0.632 multiplied by the EMF, which is 400 volts. After one time constant, the potential difference across the capacitor is 253 volts. Now we want to know when the voltage across the capacitor is 350 volts, and for that we are once again going to use the formula for the voltage across the charging capacitor. We want to solve this equation for time, so the first thing we do is divide both sides by the EMF. We get Vc over E is equal to 1 minus e to the negative t over Rc. We're trying to solve for t, which is stuck in the e to the negative t over Rc. What we're going to need to do is take a logarithm on both sides of the equation. And remember, we can't take the logarithm of a negative number. So, we multiply both sides by -1 and add 1 to both sides to get e to the negative t over Rc is equal to 1 minus Vc over e. And now we can take the logarithm of both sides. We get minus t over Rc is equal to ln of 1 minus Vc over e. Now we solve for t. The time that we are looking for is equal to negative r multiplied by c multiplied by the logarithm of 1 minus Vc over e. Plugging the numbers in, minus 4 mega ohms multiplied by 2 nanofarads multiplied by the logarithm of 1 minus 350 over 400 is 16.6 milliseconds. Now let's find the time constant for the discharging part of the circuit. Multiplying the resistance by the capacitance again, 2 nanofarads multiplied by 10 ohms is 20 nanoseconds. When the capacitor is discharging, the voltage across the capacitor is equal to the voltage across the flash bulb because there's nothing else in the circuit. So we're going to look for the voltage across the capacitor when the time is equal to the time constant. The formula for the voltage across a discharging capacitor is the initial voltage multiplied by e to the negative t over Rc. And when t is equal to the time constant, we get V is equal to V0 e to the negative RC over RC. E to the negative RC over RC is e to the negative 1, or 1 over e, which makes the voltage across the capacitor after one time constant 0.368, that's 1 over e, multiplied by the initial voltage. 0.368 times 350 volts is 129 volts. Finally, let's figure out how much time it takes for the voltage across the capacitor to drop to 10 volts. For that, once again, we will use the formula for the voltage across a discharging capacitor. And once again, we are looking for time, which is stuck inside the exponential, so we will need to rearrange things and take a logarithm on both sides. Dividing both sides by the initial potential difference, we get V over V0 is equal to e to the negative t over RC. And taking the logarithm on both sides, we get that the logarithm of V over V0 is equal to negative t over RC. Solving for t, we get that the time that we're looking for is equal to minus the resistance multiplied by the capacitance multiplied by the logarithm of the final voltage over the initial voltage across the capacitor. Plugging the numbers in, minus 10 ohms multiplied by 2 nanofarads multiplied by the logarithm of 10 volts over 350 volts is 71.1 nanoseconds. That's a very short time, but of course we are using a flash. And here you have the solution as it's written out on 2 pages. Spread the joy of physics!